models. Let's start with abstraction. Model is always the main effect of model is that you get a lot of abstraction. So what is abstraction? If you try to count those matches here, usually I ask how many matches can you see here, and most people answer 70, 50, 100, but you don't know exactly. If you have a look at the same picture now with the same count of matches, you immediately see that it's 123 matches. So what happened? We created an abstraction, a pattern. We used a pattern. A pattern always is an abstraction. You leave away the orientation and the position of the, or reduce the position of the matches to a certain pattern. By doing that, you get an abstraction for a certain use case, in this case, to count the matches. It's only used to count the matches, not for another purpose. And that's part of the abstraction, is that you always aim an abstraction at a certain goal. So that's an example for a pattern to use for abstraction. And a real world software system doesn't more look like this. And to prove it, I have generated from a huge project. I've generated a class diagram, and this looks like that. So it's a couple of thousand objects or classes and their relations. So it's basically worthless to really understand your software. So it doesn't mean that UML diagrams are useless, but it means that if you have to use the wrong abstraction or no abstraction, also diagrams do not help. So it's important to use the right abstraction to understand your system better or your problem better. So abstraction and automation with model-driven development and tests, that's something that can help. How does it work? So in the end, you always want an executable. So your software is an executable that runs on a certain chip. In this case, that's a hex code of a STM32 processor. Very low abstraction, a lot of details about how do I explain it to the processor. So what does the processor have to do? What does he have to calculate, and so on. And so that's a very low level of abstraction, but it's needed because the processor understands this language. To be able to explain it a little bit better to human beings, or to create this a little bit better for human beings, we invented C programs, C programming languages, so or other programming languages, high-level programming languages. So here you explain the logic of the program, and in this case you can see, okay, there's a case statement, standby on, switch to a trigger, and so on. So this could be something like a state machine or something like that. So that's a really technical description of what does the program have to do. But what we really want is to describe it on a high level of abstraction. We want to describe the what does it have to do, not how. So, and those are steps of abstraction. So from executable to the C program, I leave away the information that's needed for the processor. And from the C program to the model, I leave away the information, how exactly do I implement it? I don't care. If I want to talk about functionality, I'm talking on the model level here. So we have two steps of abstraction. And in the other direction, I can use, for example, code generation or interpretation to generate the C program in this case. And then from the C program, I can compile the C program into an executable to add the information needed for the processor, for the microcontroller. So, and that's an automation step. So abstraction in the one direction, in the other direction, automation. This helps a lot to work on a higher level of abstraction to really talk about what do I want to do and not how. So let's have a focus a little bit more on the different test levels and methods we can use for embedded systems. So let's have a look at At a typical embedded system, we have the electronic control unit, so microcontroller with software, the software created by you, and software units and so on, and the drivers, and they control some power electronics, sensors, actuators, and so on. And on the outside, you have the system, the real world system you're controlling, a motor, a pump, a hydraulic system, and so on. So on the lowest levels, you can use a unit test tool, for example, to test a single C module or classes, also a software integration test. That's something you can do really good with unit test tools. One level higher, on a microcontroller level, that's the first level where you actually can test the complete software stack, including the drivers. And on this level, we call this a hardware software integration test. So it's the smallest possible hardware in the loop test. One level up, you have a big hardware in the loop test, if you will, including already some sensors, actuators, eventually power electronics maybe, and so on. And on the highest level, you have a system test that really includes the rest of your system, mechanical, electrical system, and so on. So the problem is from unit test to the system test, the effort to create those tests and to run those tests increases exponentially, basically. So, and it's also really hard to automate a system test, and it's really easy to automate a unit test. But a unit test is not sufficient, and a system test is just not fast enough. So right in the middle, we can run a hardware-software integration test, a hill test, and so on. And now let's have a look at what do you need for those test levels and how can models help to do this. So for every component under test or system under test, whatever it is, a C class or even a complete system or something in the middle, you always need test cases and you need interfaces to be satisfied. So for example, if you have a C component you want to test, yes, you call your functions, but at the other end of your C component, you have a lot of includes and a lot of functions that need to are called by this C module, and they need to be there, because if not, it doesn't even compile. So you need stubs and mocks, and on top test cases, and on the bottom stubs and mocks to satisfy the interfaces. That's for a unit test. And a unit test usually is a synchronous test, so step by step, it blocks the execution, waits for the return, and so on. The problem is, in case of an integration test or a system test, you need asynchronous test cases. So because you have a highly concurrent system, you need asynchronous and highly concurrent test cases. And at the other end, to satisfy the interfaces, it's not sufficient just to have stub functions or mock functions that just return predefined values or something like that. You need a real closed or open loop simulation. So for example, if you have a motor control, you need a motor to be attached to the system in order to run. If not, you fail immediately, the system fails immediately, and you do not even get to the point where you actually can test something. So you need asynchronous test cases and closed and open loop simulations. So you need more than just test cases to test a system. So what can you now do with such a hardware software integration test, or also with a system test? The main goal is not to test a single component like a motor control, but the integration of this component with the rest of the system, with the software system, including the drivers and electric signals. So by doing that, by having a simulation, you can put your system in almost any state to test it, just by changing the simulation to do failure injection, to change values, to destroy signals or whatever. So this enables a high degree of automation, speed, and depth in your test process. So a concrete example would be, for example, this microcontroller as a black box. If we want to test the complete software stack on the real microcontroller, we can simulate all the IOs here on IO level. And in this case, I want to create a shutdown test path for the temperature. That's what I want to test. So what do we need to do? We need to stimulate the ADC inject false temperature or error temperature, then the events cascade through your system as a black box, so we don't see that. But what we want to measure is the PWM that comes out of the system. We needed to shut down after 100 microseconds, for example, because it might be a safety critical system. So I need to make sure that the PWM is off so that the motor really stops. And at the other end of the system, I want to see whether the CAN message for this error is correct or not. So that would be a typical test case. Example for a motor control plant simulation. So in this case, on the right side, you have the motor control. It generates PWMs. They are measured on the simulation side, on the test system side, and the test system generates the expected reaction of a real motor as sensor signals, for example. And here's the motor speed that the test system calculates, that the simulation calculates. That's an example for a BLDC motor with block commutation. Just as a little example, what does it look like? And the simulation should be around between 15 and 30 kilohertz. So the problem is now, how do I create those simulation and those test cases for those simulations? So you need, in this case, a closed loop simulation to test more than just software and to test most embedded systems. Now let's have a look at types of models for test case definition. So we need test case definition, we need environment simulations or stubs and mocks and so on. So typical models for test case definition are a classification tree, for example. It's a very structured approach to generate or to develop test cases for equivalency classes, boundary analysis, and so on. It helps a lot with analysis for safety and safety relevant software. Very nice method. Then another example for test case definition in models is a state transition test. It's a really nice approach. It enables to describe you the expected black box description of the expected behavior. And from that, I can generate or derive test cases. And it's very good for robustness tests. Third method would be a sequence diagram. It's really nice to describe in a graphical way and document test cases. It provides a really good graphical view on the test cases and of the execution also. So if you log results as a sequence diagram, that's a nice thing to have. And it's also easy to understand for non-developers. That's good for communication. So those are three typical use cases for models in test case definitions. Now, at the other end, we have the environment simulation. So now stubs and mocks, I'm not going into that now for unit tests, but for integration and system tests, we need environment simulations. So there are two main types of environment simulations. The first type is event-driven simulations. You can use state machines to do this. That's a typical approach. For example, implementation of protocols that you need for tests or state-based environment simulations and so on. Another type of simulation is a data flow model. For example, a MATLAB Simulink model, a continuous model for loopback control, for motor plant simulations, and so on. They are really good for this kind of closed loop simulations. So now let's have a look at one example for test case generation, state transition testing. The method is on a piece of paper. You can do this on a piece of paper. Just as an example, you design your state transition test by providing a state transition diagram, designing a state transition diagram that describes from an external point of view. So it's a black box behavior you're describing. It's not the state machine you actually implement in your system, but it's the state machine that describes the expected behavior. So In this case, expected behavior for motor control could be the motor is off at the beginning, then I turn the motor on. Now, what could I do? I could now change the speed and stop the system, or the other path would be I could brake the system. I could activate the brake. Then I'm in a state change mode, and now I'm going to change to mode 1 or to mode 2. So this leads to different passes through your system, and every path from initial to end is a test case. So for example, if you want to derive test cases now from this diagram, you need one test case for the left path here, and for a complete state coverage and transition coverage, you need, of course, the other path as well. So the yellow path would now complete or give you a transition and a state complete test. The problem is I do not test, for example, change speed against mode 2. It's something I do not test now. For that, you need a combinatorial approach that gives you a bit more path coverage. So for example, if you increase the coverage now, you need, for example, this green path here, change speed versus mode 2, and the red path, brake versus mode 1. And if you go back, if you have cycles, you need even more test cases to cover this. So the green, the blue and the green test case are not sufficient to do that. On a piece of paper, you can really work good on this level for simpler state transition tests. That's a really nice method to derive your test cases. But if you want deeper tests, or if you have bigger description for your expected system behavior, you need more, and that's where we use our mini-hill and our tooling to describe the state transition diagram as a model, and from that we generate all the test cases needed to cover to get a certain state transition coverage here. So especially the path coverage. In this case, you can see with different speeds, we try out all the different paths here. In this case, the metric is an end switch metric. It's a combinatorial metric to generate test cases. So the formal description of the black box behavior on the left side leads to with code generation to the generation of a lot of test paths for different paths, but also for data combinations. That's a really nice method. It's really hard to do this manually. Imagine if you tune up the metric a little bit, you might get 100 or 1,000 test cases depending on your system complexity and so on, or even hundreds of thousands tests to get a certain coverage, especially for robustness tests. That's really useful. So how do we do this in reality now? So we have the mini-hill test board. That's the blue one here. On the right side, you see a microcontroller with your system under test. So that's your microcontroller of your product. In this case, a Cortex M4 by ST, STM32. Could be any other microcontroller, basically. And the goal is to test the microcontroller at the pins of the microcontroller. So we connect the pins of the microcontroller over this patch panel here with our test system. So the usual IOs on that level, digital, analog, SPI, I2C, all the low-level bus systems, PWM, of course, for motor control, and so on. And on the left side, we have the test cases and we have the environment simulation. We have, in order to do this on a model base, we have a development environment where you can describe the test cases as well as the test models as models. From those models, we generate C code, compile it, flash it to our execution system here. Then we run the simulations and the test cases directly on the board because it needs to be hard real-time. For example, for a motor control, you need hard real-time simulation. And at the other end, we log the results and we transform them to diagrams, because diagrams are easier to read for human beings and easier to interpret. So that's why we use a lot of diagrams, not only for describing simulations and test cases, but also for the analysis after they failed. For example, you need to analyze what happened, and then you learn and iterate. So those are all models basically. I'm going to use this setup now to show you a little demo. So my demo is in the system under test. I have a Cortex M4 STM32 with a motor control. It generates 3 PWMs. Here I have the motor simulation. It generates Hall signals. On the other end, I have the motor controller that runs against this simulated system. I have a simulated temperature sensor as an analog sensor. It's also a model element, and we have a UART protocol also as a model, to control the speed, for example, of the system under test. So now let's jump into the demo. I'm going into my development environment for the tests and for the simulations. So basically everything inside here is, so that's my live demo here. So that's your system under test with the complete software, with the drivers, with the application software. As you deliver it to your customer, we connect this with our mini hill, and here on this side I have a motor simulation and the test cases. So we're talking now about the software running here because we want to demonstrate the software testing part and the simulation part. So now everything in here is generated as C code and compiled. So we start with the IOs. So on lowest level, I have analog adapter, digital adapter, UART adapter. I have adapter to capture the duty cycles of the PWMs. I feed the results of this measurement into the motor simulation. So motor simulation is executed on every PWM cycle, calculates the speed, and the speed is fed into the whole generator that generates the digital outputs. Now, we're using here models to describe, in this case, state machine with the motor simulation. So for example, if the PWM input changes, we memorize this as a member variable, and then we calculate the new speed, and we propagate the new speed to the whole generator. So that's also a model element, as you've seen before, the whole generator. That's the interface to the whole generator, and I can change the speed, I can change the direction, and so on. By that, also doing failure injection. So I can test more than just the happy path, because I can modify the model if whenever I want. So for example, I could add, I don't know, 10 RPM to the speed, and by that breaking my system, and I would expect that my system under test failed. Okay, so that's how we can describe the event-driven behavior. You could also now generate a plant simulation, or have a manual plant simulation and integrate it into this model. So, and now I have an environment simulation, and now I need test cases. The test cases, for that we also have a modeling language that's deeply integrated as well. But that's not a state machine now. It's so-called, the language is called CAGE, for case generator. And by doing steps and sequences, we can describe test cases. Again, here we describe as a textual model test cases, test steps. For example, one level higher, also the sequences. And here you can see the generated sequence diagram. It's generated directly here from the text. So if I change the textual model, the sequence diagram is updated, because as human beings we understand those sequence diagrams better than the textual representation, especially if it gets more complex and if the test cases get longer. So that's how we describe the test cases. Now, that's something you can do step by step now. Helps a lot to have those models here. But we want more. We want this combinatorial approach. So let's have a look at a state transition test. So state transition test, just a little example, would be, in this case, a very simple example. I have a state transition diagram that uses those steps and sequences I've shown you before. You can reuse them for the state transition test. And I have an initial test path here. So it's a state transition test. It's pretty simple. So you need only one test case. If I generate the documentation, you can see this here. That's the test case. You can do this manually without any problem. But if you say, now I have a second path here, for example, I have a second path to the state 2, and I have another path to state 3. So now I need more than 2 test cases. So let's generate the documentation again. And let's have a look at what happened. Of course, the test cases are directly generated in C code, but it's better to analyze this with the diagrams. Here you can see now we have 3 passes. We cover all the states in our diagram, state 1, 2, 3, and all the paths here. So the path elements, the transitions. But for example, we do not cover path 2 versus path 1. So path 2 versus path 2. Yeah? There's something missing. So we need one test case more. So if we increase the metric here to n switch 1, that means it makes a little bit more combinatorial effort. And now I'm going to generate this again. And now I expect that path 2 versus path 2 is tested as well. So let's have a look, path 2 versus path 2. And so on and so on. And now I can, for example, before I go to the end, I say, I want to do this again, maybe with different parameters or whatever. So let's go back to state 1 and try it again. So now I'm going to generate this again. And here we see now we need 7 test cases, because if we go back, we need to run certain tests again, because we want to run in the second run also the combinatorial paths. So if I up this to n switch 2 or 3, it doesn't explode, it gets a little bit bigger, but it's a really good method to generate a lot of useful test cases without a combinatorial explosion. So, and in the end, I'm going to show you a real test case now. That's a simple one, but that's a real test case for our motor control system. I'm going to demonstrate you. And here, for example, at the beginning, we set certain speeds, and then we let the same test cases run with different paths, of course, for different speeds. And if I want to change, let's say I want a 99% speed, I add this, and now I have 4 speeds here, and so on and so on. So, and now I get, I don't know, 5 or 10 test cases more. So in the end, what you get is from this diagram I've shown you, you get, in this case for n switch 1, you get 15 test cases. They're also generated as C code, so you do not have to program them manually. And that's again the documentation of what is generated as test cases. So that's the detail level documentation. Here you see all the steps and all the states of the state transition diagram here. Okay, so let's run this just as a last step. I'm going to run the system, and again I'm going to pull or deactivate or deconnect a connector here, maybe the UART, while it's running, and I'm going to connect my execution environment here now to the mini-hill board. I'm going to run the test, and while it's running, I'm going to pull the plug, and it should run now into a problem here. I'm reconnecting it. So now it's good again, and here you see the state transition tests. So they are running all those combinations I've shown before. And now in the end, you can use the generated diagrams again to debug, because that's now the test result. It's not the specification from before. It looks the same, but it's not. It's the executed test case. In this case, this test case failed. So if I click on that one, just a second. If I click on that one, I get in the development environment exactly the place. It jumps to the place where the step failed. So that was, in this case, the activate motor control. That's exactly this step here, and that's exactly where it failed. It failed. It did not receive the UART command or the answer from the UART channel because I deactivated it here with this cable. That's a UART cable. Good. So that's it so far. That was the demo, and now I'm going to show you a little conclusion. So models for testing help to work on a higher level of abstraction. That's pretty generic for models. You can understand and communicate problems and solutions much better on a higher level of abstraction. So you can communicate better in your team, and you can derive and generate test cases in a more structured and efficient way. And you can speed up the development of environment and plant simulations by using models, because it's just a faster development method here. Good. I hope you enjoyed the topic today. If you have any further questions, don't hesitate to contact Michael Weiss from Hitex or myself from PROTOS, and we're happy to answer all your questions afterwards.